got an enlargement question here, but the scale factor is a third. Now, when you enlarge by a scale factor 2, 4 becomes bigger. When it's less than 1, it actually becomes smaller. So I'm expecting to draw my shape kind of in this area here. Let's start out by writing down the centre of enlargement on the grid. So it's -1, 5. It's going to be here. And I'm going to then draw some ray lines just to kind of remind myself and you what's going on with enlargement. See enlargement like as a kind of a projector that's projecting out, and that's what happens especially with old school films. You have a projector at the back and it'll project onto a big cinema screen on the front of the cinema. Does that still happen today? Perhaps there's different technology. And what you end up with is a bigger triangle going on, and it'll maybe be twice as big, and it will look a bit like this. That would be if it was a scale factor of 2. And instead of going like from here to here, you would go twice as far. You'd go here to here, and you'd multiply that length by 2. We're going to do the same sort of thing, but we're going to be multiplying by a third. But there's a slightly different way of doing it that's a bit more effective, and that is to count the squares. So imagine I'm at my my point of projection, my centre of enlargement. Now I want to count how many I go up and along to get to each corner. So I'm going to go up 3. I'm going to go along 1, 2, 3, 4, 5, 6. These are numbers that I can multiply by a third. So instead of going up 3 and along 6, I multiply them by a third, and I'm going to go up 1 and along 2. And this is going to be my new coordinate for my left-hand part of the triangle. Actually, that is enough. If I want to do this quickly, I know that my triangle, instead of being 3 along, I'm going to multiply that by a third, and it's going to be, just trying to get there, it's going to be 1 along. And then instead of being 6 down, I'm going to multiply that by a third, and it's going to be 2 down. And that is my triangle done. If I want to be extra careful, and I think that is being careful, to be honest, because it's quite easy to make mistakes if you do the counting squares. That is definitely correct. I can even see the lie on the line, so that's pretty good. If I just want to maybe check this one though, let's just do it. Again, count how many I go down. It's going to be 3 down. This time it's going to be 2, 3, 6, 9. It's going to be 9 along. Multiply each of those by a third. It's going to be 1 down and 3 along. And that will indeed take me to here. So that's really good. I know I'm correct. It lies on the ray line. You don't have to draw the ray lines in. You can just count squares. There's a few different ways of doing it, but that is definitely the answer. Right, let's move on in this question. This question sort of does enlargement, and then it just decides to chuck in a bit of scale factors. Prism P, so it's completely unrelated now. Prism P and Prism Q are similar. What does similar mean? It just means that the lengths are multiples of one another. So for example, you get similar triangles or similar shapes, and you might get like squares are similar, for example. So here's a 2 by 2 square, here's a 4 by 4 square. The length scale factor is 2 because I multiply my lengths by 2. Now it says the ratio of the surface area of prism P to the surface area of prism Q is 1 to 3. The height, J says the height of prism P is 1/3 of the height of prism Q. Explain why he is wrong. Well, this comes into finding area and length scale factors, the relationship between them. If the length scale factor is 2, well, let's just look at what the areas would be. 2 times 2 is 4, 4 times 4 is 16. I actually see that the area scale factor is equal to 4. It's not the same as the length scale factor. That is what Jay has got wrong here. He's right that he would be correct if he said the area of prism P is 1/3 of the area of prism Q, but he didn't say that. He said the heights. So how does it relate? Well, actually, 4 is equal to 2 squared, and the reason is that I am doubling the top length, but I'm also doubling the height. So I have to times the area by 2 times 2. And for the volume, if I had a cuboid, I would do, if the length scale factor was 2, I would multiply the volume by 2 cubed because you've got all 3 dimensions being multiplied by 2. So in fact, how does the height of prism P relate to the height of prism Q? Well, it's just the thing in reverse. So if the area scale factor is 4, then the length scale factor is the square root of 4, which is 2. Or in this case, the height of, I'm just going to call it P, it's not 1/3, it's the square root of 1/3, which is just 1 over the square root of 3 of Q. And that's true in general. So the height of P, it's always the square root of the length scale factor. I'm just going to put that in a bracket there, but that's absolutely fine. Okay, now it does throw in a bit about the volume. The volume of prism Q is 86 centimeters cubed. That's the larger one. How are we going to work out the volume of prism P? Remember, they are similar shapes. So we've got that we've just worked out the length scale factor. It's equal to 1 over root 3. The area scale factor, we would square it. The volume scale factor, we have to cube it. So it's going to be 1 over root 3 cubed. And therefore, the volume will equal this volume scale factor times 86. I'm just wondering whether I explained that in enough detail. I think I'm just going to do a little bit more. I mean, that's going to be the, no, okay, I'll get the answer and then I'll just explain a little bit more. So if we have 1 divided by the square root of 3, that was the length scale factor. I'm then going to cube it to give me the volume scale factor, and I'm going to multiply that by 86. It's going to become smaller. It's 16.550, which I think I'll round to 16.6. Okay, that's the answer. This is just a little bit more of what's going on. Okay, let's say I've got a cube that's 2 by 2 by 2 and a similar one that's 4 by 4 by 4. So the volume of this now would be 2 times 2 times 2, it's 8. The volume of this bigger cuboid would be 4 times 4 times 4, it's 64. You can see that the length scale factor is 2, but the volume scale factor is 8, or 2 cubed. That is what happens because all my dimensions multiplied by 2, I have to multiply the volume by 2 cubed. If I have, and then the opposite is true. To go from the bigger one to the smaller one, I'm going to have to divide by 2 cubed. But that is exactly the same as timesing by 1 over 2 cubed. So that's where the 1 over bits come into in this question, because I could divide by 3 to get the volume, but I've decided to I could divide by 3 to go from one area to the other area, but that means I would divide by root 3 to get the length, or divide by root 3 cubed to get the volume, and that is the same as times by 1 over root 3 cubed. Okay, hopefully that makes a bit more sense if you weren't too happy, but I think this is a tough topic on GCSE, getting your head around length, area and volume scale factors, but hopefully this helps if you were a bit unsure. Hopefully you managed to understand and get this answer here.